All right. Good morning, everyone. And in the US, good afternoon and good evening to everybody around the world. Welcome to Tuesday's session of TestConX 2021. I'm going to start with the marketplace report. Ira is going to be the presenter here. Ira Feldman is a principal consultant at Feldman Engineering Corporation, where he brings high technology products and solutions to market. He has been involved with the test industry for many years, and is the general chair of TestConX. Earlier in his career, he managed a global team responsible for integrating HP Agilent, now Advantest test systems, into customers' manufacturing facilities. Then at NanoNexus, a photolithographic-based probe card startup, he managed product management, applications, and design groups. Later, he was a vice president of business development at Microfabrica, where he worked with leading probe card companies to create very high-performance MEMS-based probe card solutions. With his broad knowledge and management experience related to high-volume manufacturing and high technology, he is engaged on a wide range of projects, including technical marketing, strategic planning, product generation processes, and business development. Ira earned both a BS degree and a Master of Engineering degree from Harvey Mudd College. With that, back to Ira for the marketplace report.
Thank you, Ramon. So it's my pleasure to give everybody an update on the marketplace, and we're going to look first. We'll talk a little bit about the Internet of Things in our future. I'll talk about exploding applications, test challenges, edge compute, some additional test challenges, and then IoT in our factories. And then, as is our tradition, I will provide socket market data. So I think we've all heard the Internet of Things is coming, is here. I've previously shared this forecast from 2014 that predicted 50 billion IoT devices currently in 2020. But as we've seen, the numbers are not quite that high, but there are substantial growth in devices, billions of devices producing exabytes a month of data, typically wireless, very cost sensitive. So bringing the numbers a little more up to date, these numbers from IoT Analytics actually come in at just about 20 billion units in 2020, a little short of the 50, but other people were forecasting or reporting upwards of 35 billion units in 2020. But 2020 was really a very important year based upon all the data sets. In 2020, the IoT, what we think of IoT, exceeded the number of connected devices that are the more traditionally connected devices, i.e. our smartphones, our computers, our desktops, laptops, tablets, and things like that, in total number of units. So in 2020, the IoT devices exceeded the traditional phones and computers. And looking at the data, and this is total devices connected, not shipped, but looking at the data, the phones and the computers are going to stay constant at roughly $10 billion a year. So what this means is that people will continue to replenish these on, let's say, a 2 to 4 year cycle, but there won't be a large growth in the total number of phones and computers. Where the growth, and IoT Analytics is showing about 13% CAGR, will be is in the IoT. So let's focus on those devices. So as consumers, we're quite familiar with IoT devices. We may not always think about them as IoT devices, but they're clearly pervasive in our life. We have multiple smart speakers, we have color changing light bulbs, we have mesh routers, we have air quality and other monitors, weather stations, we have thermostats, smoke detectors, remote control outlets, door cameras, smart locks. I actually have a internet connected scale. So these are typical devices. And then people also have things like robots for entertainment, or maybe a room cleaning robot. Some simple things like Amazon had the dash buttons. You push the button, you got more laundry detergent or whatever it was keyed to. Smart watches, smart remotes, location tiles, the new Apple AirTag or the Tile. So I've arranged these on the slide. The ones on the left are higher power. They typically line powered, typically stationary. The ones on the right are more battery powered with increasing mobility. And then obviously you have some in the middle where they may be battery powered, but not as mobile. And the user does need to charge the batteries. I need to charge the batteries in my scale about once a year, but power is a factor, so I've ordered them this way. These are the consumer devices. Obviously, there's a lot more on the commercial side. They're more specialized, like vibration detectors for equipment for proactive maintenance, HVAC, heating, ventilation, and air conditioning sensors, where there might be an array of sensors throughout a building to try to reduce the number of hot or cold spots, traffic monitors and things like that. But we're clearly familiar with a wide range of IoT devices in our lives. And I'm sure many of us on this call have one or more of these kind of devices. So when I look at these, they all have three attributes. They're all internet connected, and it's typically done with wireless. And once they're connected, once you've done the setup, you tend to not have to touch them. You know, they automatically connect if they're a mobile device, or they stay connected in your home. So they're internet connected. They all interact with the world. They either sense, control, and or display information. So they all do one or more of those. And the other general attribute is they're all ubiquitously present. You place them at the point of use. They're intended to be deployed at high volumes, and related to that is low cost is the target, so that the volumes can be higher. And as we talked, power efficiency, they're often battery operated, or they use energy harvesting or solar cells for long periods of time to either reduce or eliminate battery replacement. So they all have these three attributes. Now, this is important when we think about the test challenges. So when we look at the test challenges, these are topics that are near and dear to us here at TestConX. We talk a lot about a lot of these test challenges. Wireless, yesterday we talked about 5G, millimeter wave connectivity. We've talked about Wi-Fi, Bluetooth, all the different standards. So the connectivity is a test challenge. We've talked about MEMS sensors and controls, the test challenges related to those. We certainly talk about the challenges of doing things at high volume and at low cost. And we also touch upon power efficiency in terms of battery operating and energy harvesting. So all these IoT devices have a combination of test challenges. So each and every one of these is challenging in themselves, but the IoT devices have them all wrapped into the devices and the products. So these are challenges that have to be solved to bring these products to market. And just as a reminder, these sound simple, but everything is quite complex when I look at things like batteries. You know, battery supplies, you know, we all like to think that a battery is a nice 1.5 volt constant DC power supply. Turns out batteries fluctuate in voltage as a percentage of how much capacity is left. They fluctuate in voltage as a function of how quickly you draw the power out. They fluctuate in temperature. They fluctuate over time. So batteries are fairly inconsistent. They're not anything near the power supplies in our ATE equipment. that have sensing, and they're very controlled and accurate. Batteries fluctuate. So one of the challenges in building IoT devices and testing IoT devices is how do you properly characterize and test when the input voltage goes up and down and may vary from moment to moment. So this is a real challenge to make sure that we fully characterized and tested our devices. And it's a challenge for the people developing the products, especially if you want to make it a low-cost product and you don't want to necessarily add a power management IC to the device. So this is just a typical set of challenges for IoT. So beyond the challenges, let's talk about today's cloud intelligence and cloud computing. I think everybody here has a current generation smartphone that has a wake word. So if we say, hello, Sarah, okay, George, or Alexander, they wake up and they trigger. And then they take your voice response and they go off and do something useful. I'm not going to use the real phrases because I don't need everybody's devices to wake up. On the Apple iPhone, which I happen to have, they run an always-on processor. So when they hear, hey, Sarah, it wakes up. A deep neural network is always listening to the microphone, and it detects that phrase. That has been trained based upon my voice. So if my spouse says that phrase, my phone does not wake up, but it is trained on that voice. But what really happens is this always-on processor runs at very low power to save the battery of the device, but it wakes up and then it's triggered and, it's always on, and it triggers the main processor to wake up. The main processor then captures the audio, packetizes it, and sends it to a cloud server where they're running additional deep neural networks and machine learning at a very large scale to interpret those audio packets, and then returns the results to the smartphone. So it tells the smartphone, here's the information to display, here's the action to take, here's the web search content, or whatever. But this setup today requires connectivity to operate. There were some earlier generation systems that had very basic commands, maybe 6, 8 commands that the phone itself could do. But today's implementation ships all the audio off to the server to tell the phone what to do. And this is how we're getting the intelligence in the current devices. And clearly the compute power at a smartphone is significantly larger than a typical IoT device. So all our IoT devices are doing something similar. They may be sensing, but they send the data up to the cloud to figure out what to do with it, and then they take appropriate action. So that's today's model. All these devices are reliant on a connectivity to a data center to be smart. So if we look at this in terms of an architecture diagram, we have thousands of server data centers and millions of servers. And then we have what's called the fog as part of the cloud, where people are working to build smart nodes closer to the edge so that you can reduce the latency and speed things up. And then we have billions of edge devices. But what the trend is to try to do is edge compute, increase the amount of intelligence and computational power in these edge devices so that we have faster results, lower latency, power efficiency, because it takes a lot of data, a lot of power to move the data from these edge devices to the cloud and back. And more importantly is scale. So if you have billions of devices, that's billions of connections to data centers that have to be, enabled and maintained. either through Wi-Fi or advanced networking as 5G or maybe soon 6G. So there's this connectivity that has to occur for these devices to function. And another key advantage of moving to edge compute is increased privacy. So if all the data stays on your phone, then there is no leakage of your data through to advertising networks or even to your ISP that may be looking at your packets. So there's some advantages to doing the compute here in the cloud, excuse me, here in the edge and not in the cloud. So in order to do the smarts at the edge, there are a number of companies working on new classes of devices that are tuned for machine learning. So for example, BrainChip has announced their Akita neomorphic system on a chip. There are other companies working on neomorphic processors, both for in servers and for IoT and mobile devices. But BrainChip recently announced in mid-last month, mid-April, they announced they work with Socionext to release they taped out to TSMC their Akita processor SoC. You see a representation here. So what's really important is that they have a traditional CPU based upon an ARM core. This is your classical von Neumann architecture, but a larger percentage of this SoC is what they're calling their neuron fabric to implement a neural network in hardware to be more intelligent and be more power efficient. And these neuromorphic processors, these are built on synaptic cross points. And this is an example of some of the test challenges in the technology of having a neuron-like array. They're typically built like a cross point. But in order to be power efficient, you can't use a traditional DRAM, CPU, or GPU because you have to take the data from the DRAM and move it to the CPU or GPU and do the matrix math and move it back and continually do this. It's not terribly efficient. So most of these architectures are using new types of memory that do in-memory compute. So this means the memory cells are able to not only store the data, but they are able to do calculations. And this is based upon the physics of how these memory cells operate. So here is a rogues gallery of some of the newer upcoming memory technology: resistive switching RAM, phase change memory, spin transfer torque magnetic memory, and ferroelectric memory. And as you can see, they have different physical operation, either, the voltage changes and the current, or the voltage resistance, or the voltage polarization. None of these are analog. So actually, none of these are digital. They all have a curve to them. So this curve allows a calculation. So if you want to add more and it's RAM, maybe you increase the voltage. So then the current goes up, so that basically increases the value in that memory cell. So these architectures are using things like in-memory compute RAM to make it efficient so the data doesn't have to move, and that allows them to make these ultra low power. But of course, these all have test challenges. These are not classical von Neumann architectures, and they are not binary. Even though they're they have digital outputs in the system themselves, these rely on a lot of analog state data. So these are challenging for test, and they're certainly challenging for using a BIS strategy. So this is an area that has to be overcome, and there's additional work that needs to be done in this area. Another set of test challenges is that these devices are relying on advanced packaging. For example, if you look at the brain chip Akita design and some of the marketing literature, one might wonder whether the blocks shown on the diagram 2 slides ago are IP blocks in a traditional design where IP is licensed and the IC is built as a monolithic unit, or as is currently being discussed for a number of applications, the concept of chiplets, where you buy IP as a physical piece of silicon and you integrate multiple ones together. So if I actually go back for a second, if the neuron fabric is built in 28 nanometer, and that might be a physical chiplet, one piece, and the CPU might be built in another technology, maybe 12 or 7 nanometer. And similarly, the different functions may be built in different process nodes that have the characteristics desired or the cost performance desired. So that possibly these devices will be built using chiplets, but nevertheless, this advanced packaging is going to require increased testing, typically additional test insertions, and we will see extended final/package tests, and certainly system level tests will become even more important to make sure that the entire device operates at full spec. So these kind of devices to do compute at edge have all the challenges of the IoT devices, plus the new architectures, plus advanced packaging. So there are some significant test challenges as the edge gets smarter. So that's a look at the compute at the edge, but we should also take a moment and consider what the implications are for IoT in our factories. So for example, today we do a lot of data mining, big data. I look forward to hearing from Rahima in a few minutes on her presentation about big data. But that's typically done in the data center, sometimes on the test equipment, but mostly done in the data center. But the IoT can bring the smarts down to the point of action. So a probe card may be a chiplet. On this example here, each chiplet might have some intelligence that could report that the probe card is out of spec, or the ground probes are resistive, or the yield is falling off, or the yield is not the same as other things, and do that local to where it can be sensed and action can be taken, and flag things as you go, not as a retrospective analysis, minutes, hours, days later. Or, a burn-in board, each socket could have some smarts to either give you predictive maintenance, hey, you should clean me because I'm about to fail, or my temperature is off. So there are all kinds of ways of using IoT technology in the factory, and we will see more and more of that in test and packaging operations as people develop more technology. So we should always think about, as we're going to Industry 4.0 in our factories, how to incorporate technology like IoT to accelerate the transition to an information-based activity. So in summary, in terms of markets, we'll see low growth rates for phones, computers, and tablets. We will still see the overall volume we're seeing, but we will have greater complexity, especially in tests, like as 5G is rolled out, or 6G, or whatever the new, local area communication protocol is. So we will continue to see complexity, but the total volume is not going to grow from today. But we will see explosive growth in IoT devices with complex test challenges, complexity related to moving compute to the edge, and this will bring fundamental industrial change to our operations as the world moves to Industry 4.0. So those are my thoughts on the market in general. And now let's dive into the socket market data. So we have go ahead.
Yeah, there's a question that I think is relevant. We are on the edge compute, right? We are still seeing large growth in both IoT edge devices and data center processing currently, but as processing power moves to the edge network, will the data center device demand decrease?
I think the data center device demand will, there will be more data centers, but I think they do run a fairly regular replenishment cycle. So I think the volumes will grow slightly. I don't think we're going to see a huge uptick. I think the total number of units stays constant until they can figure out how to pack more servers into a rack. I mean, there are more data centers being built, but I don't think there's an explosive growth in data centers. And one of the limiters to building new data centers is the power consumption of the data centers. Any other? Yeah. So let's go on to the socket market. I'd like to thank John West and the VLSI research team for providing us the data. This is their 2020 results. So this is the data they've just recently released for last year's market. The really good news is that we actually grew last year. We added almost $200 million in the overall market growth that had been forecasted as a decline, but last year it was up 200 million from the forecast. And so that's important. And the other thing that's really notable is in 2020, the test socket segment broke the $1 billion mark. So that is good. The overall CAGR for the market looking forward is going to be a healthy 4.5% with a 5.1% CAGR on test sockets. So very excited to see these numbers. In terms of the forecast, if those people remember last year, we were expecting a negative growth in 2020 as a result of COVID, but very happy now that we've seen the data. We were in the 10% growth rate. Overall market grew by about 8% in 2020 instead of declining. So those are very exciting news. The growth rates are not as high in the immediate future, but still 9% is rather healthy for test burn-in sockets, 6%, certainly a smaller growth in the burn-in sockets, but happy to see these numbers. In terms of the overall market and rank in overall sales, Yamaichi was #1 for 2020, followed by Emplas, Kohu, Lino, and Yokowo. So congratulations to these companies in terms of their overall market position. And breaking that down a little bit further, in the test socket market, Kohu took the #1 place, followed by Lino, Yokowo, ISC, and Winway. And in burn-in sockets, Emplas was top in 2020, followed by Sensata, Yamaichi, a microcontact solution, and Plastronics. So congratulations to everybody for the really strong results in 2020. So once again, I would like to thank John West for the data, for the market, and I'd also mention for those people who are interested in ultra low power machine learning at the edge, organization that I'm involved in is the TinyML Foundation. So you can find out more at tinyml.org. The whole branch of computing, of doing the machine learning in IoT and at the edge is known as TinyML. So with that, just let people know that there's some references for people who are interested in neuromorphic computing and also in some of the IoT test challenges. So with that, I'm happy to take some questions.
I would encourage the audience to actually put the questions in the Q&A box so we can quiz Ira, get some more information from him. Ira, in the meantime, for the test deployment of IoT devices, what is the future for IoT in like a traditional test factory environment? Can you talk about that a little bit?
Right. So interesting, when I was listening to the Cohu presentation yesterday on their interceptor design, where they're talking about putting the calibration parameters in an EEPROM in the interceptor itself, you could easily see where you could possibly put some smarts in it too. So maybe the unit would sense when it needs calibration, it could sense calibration drift, it could in addition to just counting the number of uses, it could try to look at, its performance. So I think as we're adding smarts into devices, it's not a huge stretch to figure out how to make them not just report data, but make them so they can act on data. So I think that's a good example. Certainly there's a lot of discussion about how to track material handling and lots, and unfortunately there's still factories that are running on paper. So I think as these are fully digitized, it's not just tracking via computer, but it's moving the smarts into the actual steps.
Thank you. So I have another question, right? What are the challenges for PCB manufacturing as these processors have more data and compute requirements?
So more the challenges. I think as they have more compute and more data, sometimes that directly scales to the test time, so that becomes a test challenge. And AI chips in general, not just the ones at the edge, some of them are actually becoming too hot to test, in that you cannot exercise everything in parallel without having thermal issues. So I think those are the kinds of challenges that we're getting faced with, especially as the size of the processor, the size of the memory goes up, is you want to run more and more in parallel in test mode, but you're actually constrained by the thermal performance of the device. And so then your test time drags out and your cost goes up.
Thank you. So how would the socket market structure be influenced by the change in IoT?
Well, I think the socket market itself, I mean, today is the technology is fairly well established. I mean, there are some innovations related to high frequency and high precision measurements, but none of the consumables that are being built today have any. I've not seen any with any intelligence. I mean, one thing that might be a stepping stone, for example, on an injection molded burn-in socket, I don't believe anybody's doing RFID tags, or serialization even. But one could see an easy step for tracking is to serialize, mark the injection molding, put an RFID tag. So that would be a step to help collect the data. But beyond that, maybe you put a smart processor of some sort in the injection molded plastic to do different sensing. So I think as companies develop this kind of technology, then there's an advantage to adding more value, having higher price points, higher margins, because you're delivering more value than just the contactors. We've seen this in TCUs, thermal control units. I won't say the specific company, but they said, hey, we're not a socket company. we do TCU modules that you happen to get a socket with, and they were able to move their price point up and improve their profitability that way.
Thank you. I think we are at 45 minutes past the hour in the US. So thank you, Ira.
My pleasure.
We don't have any further questions, so I am going to try and move to the, we just got one more, right? Okay, this was a question I was going to ask, and so it's been asked again, so let me ask this out. How do you deliver the higher current load with the AI sockets and transmission line requirements? As you make these chips bigger and you improve chiplets, how does the higher current load get dealt with? Because today I think sockets are at a max with where they go in current.
Yeah, and we will have, I think, some people talking about that in the contact technology session, but it's where devices used to be bond pad limited, where they were peripherally bonded. Your die had to be a certain size to handle all the bond pads you needed for the I/O. I suspect that there are classes of devices that are larger than they need to be because they had to add extra power pins. I mean, there's just some physics that at a certain current load, if you can't get it per pin, you have to add multiple pins. So I think that is an architectural decision that has to be made when the size of the device is determined. So.
Thank you.
I want to once again thank our sponsors who have made this event possible, our premier sponsor, Kohu, our emeritus sponsor, JonsTech, our honored sponsors, ISC, iWin, and TSC, our distinguished sponsors, Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec SVTCL, R&D Altanova, and UI Green, and our exhibitor sponsors, ELES, MJC, Phoenix Test Arrays, and Smiths Interconnect. So when you have a chance, please thank these companies for sponsoring, which has made this event possible and has made it available free of charge. And once again, I would like to thank Kohu, our premier sponsor, the market leader in test interface solutions for the most challenging applications, and ISC, the global #1 total test solution provider. So we thank them both for their leadership. And once again, I thank everybody for attending, and we look forward to seeing you again tomorrow at 7 a.m. Pacific. Thank you.